Okay, so last time we have discussed the Ginsberg-Landau equation, which basically is the equation which determines the mean field behavior of a system undergoing a phase transition, in which some fluctuations, weak fluctuations, about the uniform distribution have been taken into account in the form that that equation included the Laplacian term, otherwise saying the free energy expansion included the gradient. In other words, you would expect that inhomogeneous caused by fluctuations can somehow be included. Of course, this is only valid after the coarse gradient procedure, when you can introduce the field rather than the local discrete picture of a microscopic at the macroscopic level. So you go to the continuum limit, where you assume that you can introduce the field of the order parameter, and then this equation works, not before that. Now that equation can be solved in the presence of a local magnetic field, as we have seen. And what we have done, we assume that we are in a paramagnetic phase. Well, we didn't specify the phase, actually. Well, for simplicity, you can choose the paramagnetic phase, doesn't matter much. It's better to work with paramagnetic phase because it's more clear physically. So you have basically a disordered phase, but you have a local magnetic field which polarizes the spin, or better to say, induces the order parameter, which is the coarse-grained picture for a group of spins, as you remember, right? Locally, and then ask the question, what happens at arbitrary distance from this point? So what happened at this point is the information goes down, decays as a function of the distance. In other words, the polarization or the order parameter, which takes its maximum value at the point when the field is applied, undergoes a slow decay. Well, it depends on the point of view. The decay is not that slow, actually. It's an exponential decay. So decay goes as f of r is basically is proportional to the r to the power of psi divided by r, when the psi was square root of the stiffness parameter, the coefficient in front of the gradient term times the susceptibility. So all in all, it diverges as 1 of square root of tau, when tau is a deviation from GC. That we already have shown. And then we attributed this behavior to what is called the conditional probability, to find a value m of r at some distance from the origin, provided that at the origin I have some m of 0, suppose equal to 1, for instance. So that's actually the way how the conditional probability operates. You fix the value of some random quantity at some point and ask what happens to it at another point. But that is at the same time, the same information is contained in the behavior of the correlation function. Let me write it down as a product of two order parameters at different points. It is not quite exact definition. A better definition would be if I had written delta m and delta m prime, when delta m is not the magnetization itself, but its deviation from the average value. If I were in the disordered phase, the two definitions, m and delta m, would be the same because the average value is 0. If I'm in the ordered phase, I have to measure not the FL fluctuations, not the values of of the correlation functions per se, but they fluctuate. I will measure the correlations between the fluctuations. So if I had introduced the original correlation function MR and R prime, and that's actually the way we didn't discuss it clearly, but we should have done it. Perhaps I should have done it before. So you may ask yourself, if I define the correlation function like this, what should I expect when the distance R minus R prime goes to infinity? Then what you use is a well-known rule, well-known theorem in statistical physics called central limit theorem, which tells that for all reasonable interactions in the physically reasonable system, correlations between two objects separated by a distance which infinitely increases, this correlation disappears. Which means that, therefore, what is going on, you average each of the constituent quantities independently. They decouple. And here is just the clear sign of whether you are in the order or disordered phase. This average is only non-zero in the phase with the spontaneously broken symmetry. Right? If you are in the paramagnetic phase, the average value of quantization vanishes, and then this correlation function goes to zero. But if you are in the order phase, then this correlation function goes to its finite value, which is can be called m0 squared, which is a function of the temperature, such that m0 is a function of T below Tc. We have something like this. So the difference between fluctuating part of the correlation function, the original part of the correlation function, is that this term is always extracted. So we're really dealing only with this one. Or otherwise saying, we can move to the paramagnetic phase to simplify our life and do all calculations there. That's precisely what we will do. So therefore, I will recover. I will assume that the temperature is about Tc. The average magnetization M0 is 0. And therefore, I'm looking at the behavior of the correlation function M without replacing by fluctuations, because the fluctuations on M they simply coincide. So we are in the paramagnetic phase. And let us assume that it's quite enough, quite sufficient in the free energy expansion to keep only quadratic terms. In other words, the term b m to the 4 can be dropped out. In principle, it can be accounted for in a perturbative fashion. Then you will immediately develop new kind of perturbation theory. You will get a lot of Feynman diagrams. You will find many interesting things, but basically the main result will survive. So I will therefore concentrate on the free energy of the system as a function of mx. X, well, in our case, is the coordinate in the three-dimensional space, even though it can be generalized to any dimension. So this is f0 at plus integral dx, okay, dx, d3x, right. And here what I will write down will be 1/2. It is C gradient of the magnetization and plus a magnetization squared, and nothing else. I will assume that magnetic field is 0. I drop the fourth order term. So this is a very simple, perhaps the simplest possible expression for the free energy, because it constitutes the well-known Gaussian model. But the Gaussian model, you can do whatever you wish. This is a kind of free lunch in true sense of this word. This is a solvable problem, and you can solve whatever you wish. In fact, it's one of the very few solvable models in theoretical physics. Just the Gaussian model. This is why every time we want to get some results, we apply certain approximations. We do a certain approximation to reduce, presumably, hopefully, allegedly, the complicated problem to this one. So let me push the C coefficient outside. This will be gradient of m, and this will be our kappa squared, if you remember, times m squared of x, when kappa squared is a divided by c. By the way, in our case, a is alpha tau, and tau is positive because you are aware of the parametric phase. And this is just 1 over the xi squared, where xi is the correlation length. So far, so good. Well, the action is Gaussian, but the action is not negative. By saying action, I will very frequently use the term action by assuming that if I multiply free energy by the inverse temperature, it will be, I will make this quantity dimensionless, and then it has the meaning of what in statistical theory called Euclidean action is.
Are we now moving to the surface integral, or I don't know?
Say it slowly and loudly. Yes, please.
How are we moving to the surface? I see surface integral, and then
Surface? Where is the surface?
Okay, so
right. I'm sorry. Yeah. So this free energy is simple, but it is not diagonal because of the presence of this gradient. As you remember, the gradient of a function or the derivative of any function cannot be defined unambiguously if you know the value of the function just on at the simple point, a single point. To define a derivative, you need at least 2 points.
yes.
So therefore, this is the origin of non-locality. So if I have a function fx minus a of x, this means that you need the information to have about the both of this at this point and at this point. And if a is small, then you write down that this is equal to the derivative. So therefore, every time you have a derivative, you are not local in a sense. You need 2 points. Right? This is not surprising because this is precisely the way the information spreads in space. Because of the correlations between the speeds, because of the interaction between them. You don't have a collection of individual speeds which are not talking to each other. It's not the case. They're counter to each other. This is the origin of this gradient term. But you can easily transform the whole expression into a diagonal form if you take into account the fact that the standard way to diagonalize a quadratic form is to use a unitary transformation known as a Fourier transformation. So what you do the following. You write down m of x is 1 over the volume sum over k exponent a pi x, and this is a Fourier component, mk, which has the property, since this function is real, m minus k has to be equal to mk complex conjugate. Is it clear? Shall I explain it in more detail? It's clear, right? Or is it not? This is a real function. If I take a conjugate, I will invert the sign here. To recover the sign, I will need to go from k to minus k. So this is why this should go. Right? Yeah.
So we have now consider mx by constraint procedure as a continuous function.
Of course.
But
It's
why,
here.
why is mk a discrete one?
Why I put everything in discrete one? Just to count it? Well, it's the standard thing. Well,
Like we could have also used like integral.
wait a second. So you wanted me to write down something like the 3k divided by 2 pi divided to the power of 3, right? Something, or maybe 3 halves. I don't know. It depends on well, you have to count the number of k's. You want to number, to label the momenta and have a tool to count them. In the continuum limit, you don't have such a possibility. But we know that if we have some kind of boundary conditions, suppose periodic boundary condition for a function f(x) plus L large is f(x), when L is the length of your physical segment, you assume that every time you reach this point, you repeat the whole picture again. In other words, what you do, you fold your finite segment into a circle. You compactify your space. Your coordinate now becomes not the coordinate in Euclidean sense, it's an angular variable. And then, for periodic functions, I use the Fourier series rather than Fourier integral. That's precisely what I'm doing here. Therefore, I assume that K consists of Kx, Ky, Kz, 3 components, and K alpha is 2 pi divided by L and alpha. When an alpha is an integer number, taking value 0, plus minus 1, plus minus 2, and so forth. So I quantize my momentum. If I wish to go to the continuum limit, I use the rule that sum over k of some function 5k, which is assumed to be a smooth function of k over the minimal step, 2 pi over L. If it changes very slowly on this microscopic scale, then this goes to integral according to this rule, 2 pi to the power of d space dimensionality, and here I have ddk and the same function. You forgot this rule? I'm surprised you are asking me this, honestly. From what you were asking before, I would expect that you know this. It's a standard thing. It's a standard way to count the number of degrees of freedom. If you are already in the continuum limit, what you assume, you put your system into a final box. In 1D, just a segment with ends and periodic boundary conditions. If you are in 3 dimensions, then you impose periodic boundary conditions in this direction, in this direction, in this direction, and get what is written. Okay, so this is what is, it's a standard definition. And then you can immediately figure out that 1 over the volume, the integral dx exponent I k minus k prime x gives you this Kronecker. If I had done what your colleague has just suggested, instead of this Kronecker, I would get, of course, the delta function. But there is a direct, there is a prescription how to go from the Kronecker to a delta function. The only thing you have to take into account that delta function has a dimension, whereas the Kronecker does not. Okay, so if we use this, then we can show that the integral m squared x dx is nothing but 1 over the volume sum over k modulus nk squared. I leave it to you to prove this relation. It's very simple. Just use this. And the second one, gradient of m squared dx is 1 over e sum over k squared, of course. And again, modulus nk squared. So therefore, the free energy, let me write down delta F. M. Delta F would be Fm minus F naught. Takes the following form. It is C over 2V sum over k squared plus kappa squared modulus nk squared. Now we are much happier than we were before. Why? Because we have achieved the full factorization of the free energy. By factorization, I mean it can be represented as independent, I emphasize independent, contributions of different Ks. The K space now is built up in such a way that different points, the points in K space where delta Fk is defined, are completely disentangled because the free energy is the direct sum of those. Right? There is one catch here, nevertheless. It is associated with this relation. Here in this expression, I overcount the available degrees of freedom. Why? Because imagine that I have a two-dimensional, instead of three, two-dimensional available phase space, which looks like a Brillouin zone, for instance. So the question is, if I have this relation now, m of k as opposed to m of x is a complex quantity. Therefore, it depends. It consists of its a real part and imaginary part. Right? It's a complex quantity. The complex function, complex variable, is a combination of two real variables. So instead of, and the number of k's, by the way, within the Brillouin zone, if I had a lattice, a square lattice with n lattice sides, the number of available points in phase space would also be n. It's a very well-known fact of conservation. This is the general property of any unitary transformation. Any unit transformation conserves the number of available degrees of freedom or conserves the absolute value of the length, conserves the length. By the length, I can assume, for instance, if I have some function, complex function, this integral should be invariant under all unitary transformation. And so this is why in many cases we can anticipate the answer just using this invariance. So if I replace k by k minus k here, this will not change because of this relation, right? Neither this will change. But on the other hand, the modulus of mk is identically equal to modulus m minus k. So therefore, if I choose a half of this Brillouin zone, shown by shaded region here, and take into account only those k's which belong to this 1/2, I will do the job. Because all the others are obtained from this by changing k to minus k. But for k to minus k, the modulus is the same. So therefore, if I keep everything like this, I will use I will account for independent, not inequivalent degrees of freedom twice, which is a violation of the rule. I should have exactly the same number of degrees of freedom as I had before. Therefore, I have to remove this 2 and put the sign prime. It's in here. Prime means summation over 1/2 of the allowed frequency, of the allowed phase space. Otherwise, I will have overcounting, which I have to avoid. Now, the good question is what we need to calculate. What we need to calculate is the correlation function. And the correlation function, which is mx, m0, I can write down 0 here because of the translation areas. It doesn't depend. The only thing with the correlation function depends upon is the difference between the 2 coordinates, not each of them. And this can be easily shown to be equal to what? To be equal to 1 over, let me put it as it was in the beginning, sum over k prime, exponent I, k, x, and here I have mk, and k prime, average. Here is the first observation. Because the free energy has a form of a direct sum of independent k contributions, and because for each k, the free energy depends on the product mk and minus k, which is nothing but the mk modulus squared. Only these 2 degrees of freedom are coupled by the free energy, mk and m minus k, or mk and mk conjugate. Mk is not coupled to mk itself. Such coupling does not exist. This coupling is here. That's what I wrote. Therefore, this average is the same as the average mk modulus squared, delta k plus k prime 0. This goes without any derivation, just by observing the structure of the free energy, even though you can prove it more accurately. So, yes, 1 over v squared, sum over k, our exponent, and here is the average value of k modulus squared. So this is actually what we need to calculate, with what we need to estimate. We need to estimate the average value of this modulus squared with our expression for the free energy. Now, for that, we need to define the probability. Probability of having some m of k, some m of, well, even m of x. Because m of x can be fully expanded into components, I can ask myself,
Excuse me, so shouldn't there be 1 by just v because we have integrated kind of
what?
1 by v in the second line? Just one volume should.
Why 1 by v and not v squared? We defined m of x as 1 over v.
Yeah, I think after one integration.
There is no integration.
Okay.
There is no integration, it's only Kronecker. The Kronecker kills one of the sums, and maybe it is only one. I didn't do any integration. In that case, you would be right, but not here. Yeah, so it's clear that this probability is a product of independent probabilities of having m of k. Why? Because this is kind of a probability of independent events with no correlations between them. In this case, the probability of 2 independent subsequent events is the product of the two probabilities, as you perhaps remember
Yes, sir.
from general courses, right? So, moreover, since m of k is specified by k, you need to use only one specific p, this probability function. Now, how the total probability function looks like? The probability function E of m is proportional to exponent minus beta delta f of m. So, since delta f is an additive function in terms of k, the probability will have a multiplicative structure, right, in terms of k. So therefore it will be a product of different probabilities for a given k. So therefore, I can immediately write down, I don't need this, I don't need this. Neither of this is needed. I can immediately write down the average value of mk modulo squared should be what? Should be the integral of, by the way, please notice I keep saying that m of k is a complex quantity which consists of real and imaginary parts. Therefore, it looks like a two-dimensional vector. Therefore, the integration over mk is two-dimensional. Here I write down mk modulo squared, and here I write down what? Minus beta c k squared plus kappa squared modulus mk squared divided by the normalization integral. Everything but without this term, beta c k squared plus kappa squared modulus mk squared. Yeah. So in principle, I have to integrate over the real and imaginary part independently, but on the other hand, I know that the complex plane C, when I define a complex variable, is equivalent to a two-dimensional Euclidean space with x and y being the coordinates. And therefore, I can introduce what has been invented by the great Leonhard Euler, the Euler representation of the complex number z, which that goes down just to something very, very well known. The representation of the coordinates using polar coordinates. Polar coordinates, coordinate representation of the two-dimensional Euclidean space, right? So therefore, d2m, I don't write k, I can write it, should be rho k, and d phi k. The standard measure, right? Now, modulus of k, and k is just the radius rho. So as you can see here, nothing depends on the angle. So the angular part cancels here and here. What remains only the radial part. K is just a parameter which doesn't play any role. So therefore, the average value of mk squared is integral rho d rho from 0 to infinity. This is the measure coming out from here, times rho squared, and times exponent minus beta c k squared plus kappa squared rho squared divided by the same integral rho d rho and the same exponent as a. Now you can write down 1/2 rho squared, 1/2 rho squared. Everything depends only on rho squared. Rho squared is a new variable, call it x or t, whatever you wish, and do the simple integrals, simplest possible integrals. These are those. The answer is 1/beta c k squared plus kappa squared. Now, beta is the inverse temperature. The inverse beta is just the temperature itself. But since we are close to the phase transition, you can easily replace it by this. Because tau is already hidden here. The small tau, which measures the distance, small distance from the transition point, is already here. All other things are not interesting because this will be 1 over all linear correction in tau, which we are not terribly interested in. So, your correlation function, therefore, yes, I apologize. Everywhere let me see what I've done. I've lost the volume. The volume should appear where? The volume should appear here. Yes, the volume should appear here. Everywhere. So you have to correct your calculations. There should be volume here, and therefore the correlation function should go as Tc divided by the volume, sum over k, exponent ikx, c goes out, k squared plus kappa squared. And now you immediately recognize precisely the same integral which appears. I will replace it, if you wish, by Tc divided by c, integral d3k divided by 2 pi to the power of 3. This exponent, and that's precisely gives me the same integral as we had before. So therefore, the correlation function will simply mimic the already calculated dependence on magnetization as a function of the distance, provided we had switched on the magnetic field at the origin. And that explains the meaning of this correlation function. It measures the value of magnetization under the condition that you know what is the value of magnetization at the origin, which is nothing but the that very probability we're talking about, conditional probabilities. So the result will be just the same up to the coefficient Tc, which is not interesting. In this way, so you find out, you figure out that gamma of x is proportional to the distance in units of psi divided by the distance. You may now observe that at criticality, this should go as 1 over the coordinate, because the correlation length becomes infinite. The exponent, which is in the numerator, transforms to unity, a number. The exponential decay is replaced by pure algebraic decay. And the power law, which here fixes the one of the critical exponents which characterize the behavior of the correlation function, which is dig a little bit into the book stuff. We will figure out what are the notations for different critical exponents. I used to forget all of them from time to time. This is gamma. In this case, gamma, if I'm not mistaken, is equal to, taking account that it should be, gamma should be 2 minus d minus 2, if I'm not mistaken, plus. I don't remember. Anyway. So that's the end of the story. The correlation function is the same as the behavior of the as the solution shows the same pattern of behavior as the solution of the Ginsberg Parameter equation for a local point-like magnetic field. And this formula very, very often is called the Einstein-Zedek problem, formula, which somehow accounts for fluctuations within the mean field. So you can say that as long as mean field is valid, more or less this approach is valid too. So some fluctuations can be accounted for, but by no means they account for everything what is supposed to be accounted for. If you have any questions here, because now I'm switching to something more interesting and more complicated. All calculations are straightforward. By the way, what you have done actually here, what we have done here, it's nothing but doing the simplest path integral or functional integral. Sometimes we hear about the functional integrals as some very complicated things, but what we have done, it's a simple application of path integral for a Gaussian model, because the path integral for Gaussian models reduces the multiple integrals of usual kind. So this explains to us, especially after you have diagonalized your Hamiltonian, Lagrangian, or action, and everything becomes factorized, then you only had to figure out what happens to a single degree of freedom. All the rest is taken care of by summation of multiplication. That's it. Any technical questions? Any physical questions? Because physics is transparent. We obtain what we had to obtain. I mean, this result. This formula you told me you know already because it's a Green's function, the famous Green's function in 3 dimensions. just this asymptotics. That's asymptotics of the Green's function. For the Poisson operator, the Poisson operator is just gradient squared plus kappa squared. You can say you solve the problem of the massive boson if you are a field theorist. It's the same, absolutely. But anyway, so no questions. Everything's clear. All right. So now we are turning to a question of fundamental importance. Precisely when mean field theory is applicable? When it is good and when it becomes wrong? We already said something about it. We said that if the coordination number z is large, that means that if for a given spin, let us talk in terms of spins, if for a given spin the number of nearest neighbors is large, then the molecular field created by all nearest neighbors will not fluctuate very strongly, because fluctuations, the measure of fluctuations is inversely proportional to the square root of the number of the spins of all. Right? So the greater the z is the coordination number, the larger is dimensionality of space, the greater is the number of nearest neighbors, the better should be mean field to operate with. In a more general setting, you can say that whatever is your lattice, or hypercubic, or any other lattice, the larger the number of particles involved into the interaction volume, the better for the mean field. Because for large number particle systems, fluctuations of these numbers, and all physical quantities associated with them are relatively small. So let us find out what it means. So we know the larger is dimensionality, the better for mean field. Can we expect that at some dimensionality, the mean field becomes asymptotically correct? The answer to this question has been known for some time, has been obtained under very curious circumstances. I have already told you briefly about that. This is what is called the upper critical dimension. Let us call it DC. or D alpha if you wish. This is a dimension such that at all D greater than or equal to D, mean field is okay. It works. For dimensions less than this critical, no way. What we are going to show today of this upper critical dimension is 4. With all dimensions greater than 4, the mean field is expected to work. It works asymptotically well. The closer you are to the transition, the better it works. At D equal 4 exactly, it works with some logarithmic corrections. It means that when you calculate all the critical exponents, you obtain what the mean field gives you. But in dimensions 3 to 1, in the immediate vicinity of the phase transition, fluctuations take over, and the behavior of the system has nothing to do with what mean field predicts. The critical exponents go to completely different values. Even though, in some cases, there can be a range of temperatures close enough to TC, but not too close, when mean field can be expected to give good results. And we will see that. We'll explain later on why in superconductors this is precisely the case. Why the mean field is an excellent approximation in the Bardeen-Cooper-Schrieffer theory, microscopic theory of superconductors, but not for the theory of magnetism, quantum magnetism, for instance. So the first thing I want to do is just to introduce again the free energy. We are close to TC. That means that tau is much less than 1. We will assume that A, as usual, is alpha tau, B is positive, and magnetic field is 0. And then we'll write down the free energy as, let me work with delta F of M. Instead of M, I will pay tribute to the great Lev Landau, who would denote the order parameter by the Greek symbol eta. Even though you can still use M, I didn't say one more thing. The symmetry, discrete symmetry, should be Z2. That means that the Ising model, we are dealing with Ising model. And this f of eta is, now I do something more accurate. I will write down everything and then explain to you what I mean. 1/2 C gradient eta squared plus 1/2 A eta squared of x plus 1/4 B eta to the 4th of x. Full stop. So what I did, I divided by, so R naught is the same, more or less the same as A naught. It's not lattice spacing, or it's a minimal length scale in the problem. You know, if you are a theoretician coming from the field theory community, you don't have for free a lattice. You have to introduce it by hand. Because all they care about is to keep the theory regular at small distance. Actually, we do the same in condensed matter field theory, I would say. But we have a good excuse for that because we have a real lattice. Underlying lattice gives us such a possibility. Lattice is a physical reality. For them, lattice is a kind of auxiliary object they invent. They put the theory on the lattice and then remove it. So R naught, let us be the minimal distance, or whatever origin. There is nothing smaller, shorter than R naught. It's a microscopic length scale. Right? So this ratio, therefore, is dimensionless. Right? F has to have the dimension of the energy. So therefore, A should have the dimension. So I will assume that eta is defined in such a way that its engineering dimension is 1. It's dimensionless. Like a sigma, like a speed. Like the Ising speed, doesn't have any dimension. It takes values plus or minus 1. So A and B must have a dimension of energy. Now C, as you can see, must have a dimension of energy times length squared. Why? Because this is a gradient squared. And this cancels for the inverse length square in the gradient, right? Now let us also recall that alpha is of the order of Tc and B is also of the order of Tc. We had a problem once we mentioned, and you, by the way, I didn't tell you that. You all have my notes, right? If you take all the problems from 1 to 7, included, and bring it next Monday in the written form, so such that I could look through them and get some first impression of it. The problems are very simple. 8 and 9 are a little bit complicated. So from 1 to 7, this is compulsory. 8 is a star problem, 9 is a star problem. You are strongly encouraged to solve them as well, but not obliged. Let me put it like this. Needless to say that those who have an ambition to be good as good grade as possible would be especially stronger encouraged to solve at least one of these problems. Problems go first, actually. This course is mild first, and many body course which I used to give for years. Every one lecture, two lectures, and then bunch of problems from 10 to 15. Again, one lecture, the second lecture, another 15. So it was a big bunch. Yeah. But the students like it. Anyway, so everything is fine. A and B are of the order of Tc and indeed have the dimension of energy, and C is the dimension of energy times L squared. Good. Now what we will interested in is not the free energy, but the so-called Euclidean action. Don't ask me why I call it action, because when you turn to field theory, if you choose field theory for your career, which is, or at least we will dig into some issues related to field theory, this is that very action that you would expect after integrating the Lagrangian over the corresponding coordinates. But then before doing that, you have to take into account that the metric in the Minkowski space is not the same as the Euclidean space. And it causes the whole sequence of mathematical, technical difficulties. So it's much easier and much more consistent to do all calculations in Euclidean matrix by doing so-called V-rotation to work with imaginary time rather than the real time. But anyway, whatever is the origin of this term, this we'll call the action, and this action is simply defined as beta delta F, which is the same as delta F divided by the temperature, and of course, without any hesitation, I can write down Tc, because I assume that I'm sufficiently close to the critical point. Right. And now all what I need to do is to do the following thing. So it will be ddx divided by r naught to the power of b. And here I will write down C bar, simply replace all the coefficients by the bars. A bar beta squared of x plus 1/4 b bar eta to the fourth of x. Full stop. Where C bar is C divided by TC, A bar is A divided by TC, and B bar is B divided by TC. Just the same expression as before, the only slightly changed. So these two quantities became dimensionless, two parameters, because they had the dimension of energy. So the A bar and B bar are just the numbers, dimensionless numbers. So C is a fixed parameter, B is a mixed parameter, A bar does depend on tau. And this is the only running parameter in our problem. It measures the vicinity, the closeness to the phase transition point. Now, what is the main idea? The main idea is as follows. The probability of a given configuration will be proportional to this action, to the exponent of this action. So yes, it's actually the free energy divided by the temperature. So you should not be surprised. This is the Gibbs hypothesis, one of the basics of statistical physics. What is the idea? The idea is to pass to thermodynamic limit. This is very important. For an infinite system, you go to thermodynamics limit using the following trick. You rescale the coordinate and you rescale the field and expect that after such rescaling, your action will transform to some coefficient gamma times S1, where S1 is the same action, has the same form as here, in which does not contain any parameter. All the things which you observe here are replaced by numbers of the order of 1. The parameters should be excluded completely. And therefore, such an action which does not contain any parameters should be of the order of 1. It's the famous statement. I don't remember who was the first to make such. If you have an integral, suppose, from 0 to infinity, function x, and a bunch of parameters, alpha, beta, blah, 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 yes. If alpha, neither of these parameters does not represent either a small quantity or a large quantity. Because in the first case, you will expand in powers of alpha, beta, and so forth, or you will expand in terms of inverse alpha, beta, and so forth. If nothing like this happens, if all alpha, beta, and all the others parameters are of the order of 1, and you know for sure that the integral converges, the integral is of the order of 1. It may be p squared divided by 36, but it's again a number of the order of 1. It's a number. It's not a parameter. It cannot be large, it cannot be small. If nothing can be large and nothing can be small, it should be of the order of 1. The same is here. So this action will be of the order of 1, so therefore all information about the physical properties are controlled by this parameter. All information should be hidden into this gap. So your probability will transform, therefore, to this. And you know that this is of the order of 1. Now comes the question. What is the mean field theory? In the mean field theory, so by the way, this is the probability distribution for any realization of the parameter field. Sometimes we call them trajectories, because we have an analogy with the Feynman for formulation of quantum mechanics, so we like to call them trajectories. That was realization of E. And this is the probability. For one profile, you have this probability, which is determined by the contribution of this particular profile to the free energy or to the action, which you call.
It's not so clear to me what we just did here when we introduced the lambda and then we scaled the field.
When I introduced lambda, here,
Yes.
I didn't do anything, I just simply mentioned. All I'm able to do to produce is to make scale transformations, nothing else. To rescale whatever is here. What is here? What are those quantities which I'm dealing with? Is coordinates and the fields. Nothing else. All the others are the parameter of the Lagrangian or Hamiltonian, which are untouchable. They are given. I'm coming closer to the scaling ideas, if you wish. I'm trying to stretch or squeeze the function eta of R, which describes the order parameter. And the way it behaves under the stretching or squeezing reflects the property of the system. This is the first example when scale transformation start playing important role. To be more precise, if you wish. Thank you for this question. Yeah. So, yeah.
Since we have scaled both the x and eta, the scaling of x affects also the scaling of eta because it is a function of x. So.
No, well, of course, these are coupled. There is no question about it. These are not independent things. They will be coupled, for sure. But
that rho scaling
no,
of eta is...
what I should have written is that under such transformation, x goes to this one, and this function becomes the function of the new coordinate. This is what you are saying, which I didn't write here. So if I remove this, and I remove this, everything will be all right. This is taken care of automatically. So the Landau theory does not explore all the trajectories. It selects only one, the one for which the probability has a maximum. The probability of the classical trajectory as what you have in classical mechanics. You have the Lagrangian or the Lagrange functions, you have an action, and you minimize this action. You have a minimal action principle, remember, right? And you derive the early Lagrange equations. But if you look at the measure with which different trajectories contribute to physics, it's not only the classical trajectory. Many of them, in quantum mechanics, all of them contribute. In classical mechanics, only one. So mean field theory is very similar to what happens when you compare classical to quantum mechanics, in such a way that the classical mechanics, which selects a given trajectory, and the mean field approximation, which also selects a given specific trajectory, they operate in the same way with respect to something more general as quantum mechanics or exact calculation close to the critical point in the theory of phase transition. This is why the description of the phase transition goes along the lines of a quantum field theory. It is not by chance. This is because of this analogy. This is a very deep, serious reason for having this. So you assume that the probability should be maximum, and therefore the minimization of action gives you the equation that you have already done. Assume that derived is the equation which goes like this. It's a naught squared plus b a naught to the fourth is equal to 0. This is the most probable trajectory. Eta naught should satisfy this Ginsberg-Landau equation. Good question, when it is correct. If S is of the order of 1, when should you expect the most important trajectory would satisfy this equation? Because this equation comes from the condition of delta S is equal to 0. You minimize your direction. Right? It can be only the case when the parameter gamma is very, very large. Because if the parameter gamma is very, very large, the main contribution to this exponent will come from those eta for which S1 is minimal. Right? And that defines actually the way, if you ask me what happens in quantum mechanics, I will tell you in quantum mechanics, I have this. Is the action in units of the Planck's constant. And then we say, when would we expect the classical mechanics to be valid, to follow from quantum mechanics? Formally, in the limit when h goes to 0. This is very simple, very similar to what I'm saying here. In the limit when gamma goes to infinity. Nearly the same logic. Right. So, I'm not left with much time, but nevertheless, let me try to do some estimations. I don't do this, I already remember. So let me simply do this transformation. If I transform this action, what I will get this dx r0 to the power of d, lambda to the power of d, coming from the measure. From here I have 1/2 eta transformed to zeta squared. Here I have c, and here I have coordinate in the denominator, therefore here I have lambda squared. Right? And the gradient eta squared plus 1/2 zeta squared a beta squared plus 1/4 zeta to the 4th b beta to the 4th. Is it clear what I've done? This extra lambda appears from the measure of the integral, and the other thing is here and here eta appears in the second order, therefore zeta squared here, zeta squared here. An extra differentiation gives me a lambda squared because of this, and all the rest is clear. Now what I want to do, to be able to push some coefficient outside the integral, I have to insist that zeta squared divided by lambda squared is the same as zeta squared there's definitely something wrong here. Just a second. Just a second. Yeah, so lambda to the power of d. Yeah, so I can do the following thing. I can write down 1/2 lambda to the power of d minus 2. Remove this and remove this. And I can introduce, multiply by 1/2 lambda to the power of d, and again plus 1/4 lambda to the power of d. All right. And nothing else, nothing else but this. Oh. Now I have to look into my notes because I don't like a certain expression. This. Yeah, everything's fine, but of course that is the most important thing. All right, let it be as it was. And how it was lambda to the power of d. This is my lambda minus 2. Nothing here and nothing here. It's a mess, but it's a readable mess. So it should be theta squared divided by lambda. And c bar grad theta squared. Now it's fine. Yeah. So what we want to do is theta squared divided by lambda squared, right? Lambda squared, thank you, times c bar has to be the same as theta squared times a bar. It has to be the same as theta to the fourth and b bar. So I forgot to put this other coefficient. That's important. So I want to all these things to be just the same, because if they are the same, I can push them out. Right? So these give me the following conditions. For instance, for lambda squared, I obtain theta is cancelled, and here I have c bar divided by a bar, which is the same as c divided by a. This is one thing. And there is another thing. The theta squared is a squared divided by b squared, by b, a divided by b, which is the same as a bar b bar, a divided by b. If this is done, then our action takes the following form. It gives me 1 over r naught to the power of d, lambda to the power of d. And now I can choose any of these as a coefficient. For instance, this one, zeta squared divided by times a bar, and then I will be left with the integral d dx without any. By the way, this already a dimensionless coordinate because of the definition, right? You remember? Okay, you remember. Yeah. So here I have 1/2 gradient eta squared plus 1/2 eta squared plus 1/4 eta to the fourth, and no coefficients whatsoever, if I'm correct, because everything else is here. So this is precisely the action S1. This is the S1, this part, because it does not contain any parameters. And gamma, for gamma we have now an expression. And we have to be extremely careful in dealing with this. This is lambda to the power of d r naught to the power of d. Now instead of zeta, we take zeta squared is a divided by d. So it's a squared divided by b, a bar by b bar. By the way, it's better to me to keep my nose within reach. Otherwise, I may be in trouble. It's a cumbersome derivation, simple but cumbersome. Yeah. Yeah, so it's all about lambda. So therefore, it is lambda is it's c bar divided by a bar d by half. This is this one, and I also have r naught to the power of d. And I also have a bar squared divided by b bar. And this I will rewrite as follows. I will write it down as c bar to the power d by 2 A bar will be to the power of 2 minus d divided by 2. All right. And L this is divided by d bar r dot to the power of d. Okay. We're done. Excellent. Excellent. So this is a kind of nasty but still interesting expression. Why it is interesting? Because of this power. Look what it is. 2 minus d divided by 2 is 4 minus d divided by 2. Oh, you see? 4 minus d. This is the quantity which changes its sign when d goes. It's above 4 or below 4, right? So what you can do, if you plug in everything, if you remember that our coefficients b and how was it? Alpha were of the order of Tc. If you use all this, you'll find out that your gamma is given by the following formula. It is C divided by Tc R0 squared to the power of d divided by 2. And from A bar, from A, what comes out is this coefficient, tau 4 minus d divided by 2. This is the expression that you have, which you can immediately check if you carefully look. Well, Tc is the consequence of the fact that, by assumption, these two quantities are proportional to Tc. Now the question is, what is the meaning of this prefect? So there are two important things. This is dimensionless quantity, and this is also dimensionless quantity. And you want to understand what is the meaning of this prefect. This is clear. What is this? Now, to figure out the meaning of this term, is it 20 minutes already?
We have 10 minutes left.
10 minutes left. Okay, I hope I will try to come to the main conclusion. Let us recall how the correlation length looks like in the mean field theory. And the correlation length in the mean field theory is proportional to the square root of C times the susceptibility. This is what we've done yesterday, the day before yesterday, and even today. So when we solved the Ornstein-7 case, the homogeneous problem, we found out that the correlation length is defined like this, right? On the other hand, we remember that this has to be C divided by A, when A is alpha times tau, right? Which is C divided by Tc times tau, assuming the tau is greater than 1. And now the question is, what if we extrapolate this definition to the case when tau is of the order of 1? In other words, if we deviate from Tc by a distance comparable to Tc itself, which is a little bit a brutal force method, because everything so far was only valid in the immediate vicinity of the phase transition. But we're not talking about calculation, we're about the estimation and understanding of what is on. This is how we develop our intuition. If we expect that this formula, not exactly, but at least qualitatively, will make sense if I deviate sufficiently from the phase transition, replace tau by a number of 1, I will get a new quantity, which is psi naught, which is square root of c divided by Tc. What is the meaning of this psi naught? What do you think? Well, it tells by itself. It's already there. Psi is psi. Psi is a correlation length. So psi naught is also a correlation length. But where? The answer is far away from the transition. It's the correlation length, which is far away from the transition. Which means that you are deep in the disordered phase. The disordered phase doesn't even know that the system is going to undergo a phase transition. You are in the normal phase, so to speak. So this is the correlation length which is imposed, so to speak, which is formed due to the Bayer interactions. Psi naught is the length which includes all interacting particles which we describe in the Hamiltonian or action or whatever. This is the microscopic picture. You have something, you have a particle, you have a spin which interacts with others, say with nearest neighbors. Psi naught will measure, therefore, the number of nearest neighbors. It will be a coordination number. Or it may be some other model in which the interaction radius is such that the number is different from the z, maybe larger than z. In other words, psi naught to the power of d defines the interaction volume. And psi naught to the power of d divided by r naught to the power of d. Since this is the distance between the particle or the spin, that will give you effectively the number of particles involved in the interaction in your model. So, therefore, you see that C, the parameter C divided by Tc R naught to the power of d is nothing but psi naught divided by R naught squared. And your gamma parameter takes a very suggestive form. Your gamma becomes psi naught divided by R naught to the power of d times tau. Now I can safely erase all of the rest. How come to the conclusion? What we need to do? Gamma has to be much greater than 1 for the mean field to work, right? We already know this. When gamma has to be much greater than 1, then tau 4 minus d times, this is just precisely the n star, much be greater than 1, tau must be much greater than n star to the power d minus 4 divided by 2. Did I make any mistake? Did I do or did I didn't?
Should be 2 over.
This n is 1 over n. It goes here.
2 divided by d minus 4.
It should be the other way around.
2 divided by 2
d
minus
minus.
So it should be d minus 4.
2 divided by d minus 4.
Why 2? Why 2? I don't understand. Yeah. Of course. Sure. 2 divided by d minus 4. Not the other way around. Right. Or better to say 1 over n star 2 divided by 4 minus d. This is fine. Is this fine?
Yes.
That's fine. Good. But on the other hand, tau must has to be much less than 1 by assumption. We are close to the phase transition. Therefore, for all this, what is written here, to make sense, this quantity must be small. Right? So let us start with the assumption that forces which describe your system, your thermodynamic system, are long range, which means that the number n star is much greater than 1. Right? Then you immediately observe that in directions d greater than 4, you have a 1 divided by a large quantity. So this is indeed a small quantity. And this small quantity in this case is strangely denoted not by a single letter, by the GR. This is the first letters of the name of the great physicist, Nobel Prize winner, Vitaly Ginsberg, the late Vitaly Ginsberg. The same Ginsberg which is Ginsberg lambda. So this is the Ginsberg parameter. He was the first to recognize the importance of these fluctuations or its region. The Ginsberg parameter in this case is a small parameter. It tells you that if your tau is much greater than Ginsberg parameter, even though otherwise it's small, but not too small. So this determines the vicinity close to the phase transition, such that away from it, the mean field works. The mean field perfectly works in this case. But please notice I assumed that n star is large, long-range forces. Of course, you will conclude that inside that region, the mean field should not work, because this condition is very robust and tells you that this should also aside of this, and so on this. But what happens if the forces are not short-range? Are not long-range, but are instead short-range, when n star is of the order of 1, as it has to be the case in magnets. Then this quantity in the left-hand side, well, is no longer small. And this sequence of inequalities loses its sense. It cannot be applicable at all. And then the conclusion is for short-range forces, you are in big trouble. So you have only chance to survive, in the sense of the mean field theory, in dimensions greater than 4, irrespective of the range of interaction. But if d is less than 4, when d is less than 4, then and n is not particularly large, then you lose this ability to work with the mean field approximation, and you have to use some other approaches to reach the important conclusion what to be and what to do. So d equals to 4, therefore, in all this derivation gives us a clue that indeed the larger the dimension, the better the theory works. The boundary turns out to be 4. This is a kind of theoretical prediction. And the next question to ask would be, if we start going to lower dimensions, then the role of fluctuations must increase, as we already see from here. In lower dimensions, in dimensions when d is equal to 3 already, we have a problem, but in smaller dimensions, the role of fluctuations will increase. And the good question is, what is the lower critical dimension? So this is the upper critical dimension. The lower critical dimension is the dimension when the phase transition ceases to exist at all. The Tc goes to 0, roughly speaking. Only the ground state turns out to be ordered, but not any thermally excited state. And that the answer will depend on the symmetry of our problem in question. For symmetries, for discrete symmetries, it will be a one-dimensional, the lower critical dimension, dl, is 1. This is the Landau-Pines theorem, which states that There is no ordering in one-dimensional systems at all. This is why one-dimensional physics is very peculiar. But this is the discrete symmetry, discrete. But in case of a continuous symmetry, the critical dimension is 2. You may have an order in 3 dimensions, but not in 2 dimensions. In 2 dimensions, it's more or less clear because when your order parameter can vary not on the manifold consisting of a finite number of points, like Z2, only spin up or spin down, but you can explore some curve or some surface, as it is for the planar spin or 3-dimensional spin. Then, of course, it's much easier to disorder the system just by smaller deviations from the given direction of the order parameter. So if you imagine an ordered state, then you don't need to have a jump of the order parameter by its opposite value, but you can even consider small deviations, and these small deviations may also have a tendency to destroy ordering. So therefore, the larger the symmetry, the more efficient is the tendency towards destruction of the long-range order. This is why the critical dimension for continuous symmetry, like U are O2, O3, turns out to be 2. So there is no order, and this is already known as the Merwin-Wagner theorem. So we'll have to derive this all these restrictions are quite important because you don't need, if you don't know these theorems, you will naively, looking at the problem, start trying to solve it. Whereas it may be meaningless because you should know a priori that there should be no solution. If you start deriving the long-range order of new field theory in the one-dimensional Ising model, we will see next time that there is no way of doing that. There is no ordering at all. So this is more or less, I think I will repeat the last part of this derivation tomorrow because both you and me, we became a little bit tired. It's a tedious calculation. It's not a big deal, but it's a tedious one. But the idea is very simple. I again would like to repeat it to you. The idea was to represent as in this way. Perhaps you should have noticed that this would be impossible to accomplish in a finite volume, because if I had made a scale transformation of the coordinates, instead of, say, a large volume, if lambda is suppose less than 1, I will squeeze my system. So therefore, the range of integration in the new S1 would be different from what I had there. I can only expect that nothing happens because I will go to the thermodynamic limit when I'm dealing with infinities. So I don't care in this case. That's a field theoretical limit. So therefore, the whole derivation is a field theoretical one. Maybe in quantum mechanics you will be surprised to learn that, in fact, there is no such thing in quantum mechanics as going to classical limit when h goes to 0. Because h cannot go to 0. Because h Planck's constant is a world constant which takes fixed value once and for all. It's only the normalized h goes to 0 can go. You first have to make it dimensionless, like our parameter gamma. If you are able to do so, then you may find conditions under which the renormalized dimensionless h goes to 0. So this is a good example of that. We'll discuss it tomorrow. Okay, see you tomorrow. Oh, I have to switch it. This one?